Hello, Derek Hitchens again. This time looking at systems engineering case study examples and any valuable lessons for teaching that we might have found out. There appear to be two approaches to case studies, fundamentally. One is to form them around real-world situations, and the other is to fabricate them or simply make them up to suit our particular teaching purpose or need. The real-world situations are quite often based on disasters or catastrophes, and that's helpful because it allows us to understand system pathologies, what makes systems go belly up. On the other hand, if we fabricate studies, then we can set up greenfield situations where there's no legacy problems to complicate the issues, and that will allow the students to exercise their understanding and application of a taught method. And it encourages teamwork, competition, and can help them to develop a systems methodology. There's merit in both approaches. There's lots of real-world situations where there's been catastrophes, of course. One thinks of the R101, the airship, and a picture shows the Titanic in Southampton water before its fateful voyage. There's the Apollo fire of 1967, 3 Mile Island, nuclear power generation station, Challenger, Bhopal, Chernobyl, and the Thames Barrier, which wasn't a disaster but was actually built to prevent a disaster, to defend London against flooding, which can occur whenever there's a simultaneous spring tide and particularly low atmospheric pressure, a depression of some sort. So studying pathologies is good, but it's limited. While it reveals the past wrongs, it doesn't tell you how to do things right. And it's difficult to design on the basis of what not to do. However, there are at least a couple of exceptions to the rule about real-world situations. The first one I'd like to bring to your attention is the Japanese automotive industry. Excellent basis for a case study. Industrial systems engineering on a global scale. There's a reference shown there, The Machine That Changed the World, excellent book by Womack, Jones and Roos. And Taiichi Ohno is mentioned there, who was the really originator of this lean production process within the Toyota Motor Company in Japan. The other real-world situation, which is evolving and developing very nicely at the moment and would make an excellent case study, is national and international air traffic management, particularly with the advent of open skies. Worthwhile real-world situations for exploring. Then there's the fabricated or focused case studies, and they're generally about aspects of the whole systems engineering process, if you like to call it a process, from problem investigation through remedial concept formulation, design, synthesis, operation, optimization, and problem solving, which tends to in fact incorporate all of them. You can also set up case studies about the systems methods that you're going to use, and of course about the whole systems methodology, which can be seen as made up of a number of end-to-end linked methods. Experience shows that it's better to teach a systems method followed by a case study that is outside the student's current knowledge. Why? Else the student uses his or her current approaches, their current methods, and does not use and learn the value of the taught systems methods. This might not seem obvious, but it is a problem. And here are some of my favourite case studies. The first one, FarSide of the Moon. Let me read these things to you. Conception, design and organisation of a manned outpost on the far side of the Moon for radio astronomy and to acclimatize astronauts travelling to and from Mars. It's clearly a green field, if you can refer to the far side of the moon as a green field, but certainly there's nothing there at the present time. And the trick on this particular case study is that there are two completely different purposes to the outpost. Then there's the autonomous peace officer. System design feasibility study for a fully autonomous anthropomorphic peace officer capable of patrol, situation assessment, pursuit and arrest. RoboCop, but without the human contact. This is advanced technology, it's artificial intelligence, and it's complex. So this is for the more advanced student, and it's for a multitude of different technologies all working together within inside a human-sized frame. Tricky stuff, but very, very interesting. And then my third one is called Land Force 2010, which gives a clue about what it's about. This was first established as an INCOSY tutorial. It uses a full-blooded systems methodology to explore defence issues, to conceive and design an air-transportable, mobile, automated land force, including network-centric warfare, unmanned air vehicles, etc., for deployment over the Great Plains, tundra and desert areas around the globe. This is complex, it's socio-technical, it's innovative, and it's couched in a defence scenario. Let's have a look at that last one again. Land Force 2010. It consists of a number of tutorials: systems philosophy, identify, bound and explore a problem space, conceive potential system solutions, design a system solution, optimize that solution's design, prove that you've done it. As you can suspect from looking at the list, the whole set together really covers the systems methodology. Some of the things that come out of Land Force 2010 shown in these little video clips. At the top left we have a chameleon, which is a sort of mini tank. It's silvered on the sides, and the top is a moving copy of the ground that the little tank is travelling over. So from above and from the side, the vehicle looks virtually invisible. You can see a bunch of them, a swarm at the top right, with no camouflage on, otherwise there wouldn't be very much to see. And the swarm is going around a pair of knolls and coming into a linear formation to go up a defile, all under automatic control. Bottom left we have a dragonfly, which is shaped like a dragonfly so that it looks like it's part of the environment. It has video cameras for eyes, the wings are solar panels, and the tail is an antenna, and you can see some mud buildings from a desert in the background. Bottom right, much larger than the tiny dragonfly, is a raptor. The wings are also solar panels, the eyes are also video cameras, but instead of just being able to fly, the raptor can soar, and so it can go to great height, can cover great distances, and can stay aloft for hours on end. So it can undertake surveillance missions, passing the information back directly to the swarm, so that they can see what's ahead of them in terms of lay of the land, potential enemies, and so forth. It's a jolly good fun exercise. Students love it. Far Side of the Moon. It's got major logistical, organisational, communications and human issues, as you can imagine from people fairly isolated on the far side of the moon. It's shielded from Earth, which is one of the points of setting up radio astronomy there, at the low gravity encourages larger structures and dispersed interferometer arrays, for example. The method that's being used here encourages imagination and innovation. So for example, we have a three-dimensional model of the moon's surface there with a vertical tunnel covered by a transparent bubble, and from the side of the vertical tunnel there are tunnels going laterally under the moon's surface to create caverns where people will work, protected from meteorites and high energy cosmic particles. FarSide functional subsystems. The first one we can see is the operations subsystem here. We can see all the various departments or sections. We can see an operations center, which is looking after astronaut rehabilitation, training, and is linked to the astronomy control, and so on. The next one we're looking at is the logistic subsystem, and their resource management subsystem, which is obviously coupled to the logistics. And then there's the base command subsystem, which ties everything together, supervises, administers, and so forth. CPRM, by the way, is contingency planning and resource management. Note to the psychology department, which is to do with ensuring the balanced behaviour of the various people in the centre. Interesting stuff. The autonomous peace officer, it's not really like Robocop at the left, but it employs methodology and reference models. There are no human components in Robocop. He looks, walks, talks, behaves like a human peace officer, unlike Robocop, who clumps around like a machine. It patrols, secures, pursues, apprehends, reads rights like a human peace officer, which of course raises ethical questions. Should it be armed? And if so, should it have a lethal weapon? The whole exercise is tricky to non-feasible. We don't know how to actually build something like this yet. So this is for advanced student teams to cut their teeth on. Very interesting, sophisticated, up-to-the-minute technology. Interesting to look at the way you start off something like this. I would suggest you start off looking at stakeholder prejudice. Concern that the robot police officer would be ineffective. People get this idea from looking at films like Robocop, I'm afraid. For example, at the right, they suspect an inability to pursue suspects effectively. Would it be able to climb stairs? Would it be able to jump walls, fences and gates? Using that as the basis, you can work out some of the things that the APO would have to be able to do, and do well. It would have to be able to assess situations, recognize behaviour of individuals and of groups. It would have to be able to manage its operations. And there is a suggestion there that there should be safety control to shut it down should it run amok. Going back to the general idea of case studies. Case studies for teaching are best tied to teaching of particular methods in sequence, building to a systems methodology. One way to approach this, which I have used and found to be highly successful, is to split the group into teams, where the team size is between 5 and 7. So not less than 5, not more than 7. To go to 8, the team starts to break up into smaller groups. Team dynamic is quite important in this, because we're going to create a pressure cooker situation. You introduce the whole group to the particular method that you're going to use for the case study, with examples, and then you present the case study with clues how to get started, and then you set the teams to work in competition. You only tutor them as needed. Later on, the teams will present their solutions in competition, and it helps to award small, insignificant prizes to the winning team members. What is the best solution is judged by the whole group, which encourages them to be objective. And the pressure of competition actually works. I have tried this over a number of years, and it works very well. Good luck.